Hello, and welcome to the screencast on changes of state. So today we're going to talk about vapor pressure and phase diagrams and how this relates to what we've already learned about solids and liquids and intermolecular forces. So changes of state are caused by energy changes that affect intermolecular forces. And what you guys probably already know is that melting is going from a solid to a liquid, vaporization or boiling is going to from a liquid to a gas, and condensation is going from a gas to a liquid. Freezing is going from a liquid to a solid, and sublimation is going from a solid to a gas. So melting and vaporization, these are caused by adding energy, which would make them endothermic processes. And condensation and freezing are caused by removing energy. And so those would actually be exothermic processes. And sublimation is going from a solid to a gas, and so that would also be endothermic because you'd be adding energy. And the opposite of sublimation is actually called deposition. And that's going from a gas to a solid. And you've seen this happen with dry ice. When you take dry ice out of its container, you'll actually see all the smoke that forms, and that's actually an example of sublimation. This is a heating curve, and this is important because it shows what happens as you add energy to a substance. So when you're adding time, you're really adding energy. And what happens to the temperature of that substance when you add that energy. So it shows energy changes as a substance changes state, and that's the kinetic energy because it is the temperature that we're talking about. And so on inclines, you only have one state. The substance is in one state of matter. And so the lowest one is going to be a solid. The next incline is going to be in a liquid state. And the last incline is going to show the substance in a gas state. When you have a plateau, though, you have two states happening at the same time. And that's because you have a change of state happening. So that lower plateau is when the substance goes from a solid to a liquid. And as you know, that's called melting. And the higher plateau is when the substance goes from a liquid to a gas. Now, this can involve some calculations as well. So when you're doing calculations to calculate the energy changes associated with these temperature changes, if the substance is on an incline and there's only one state of matter, you're going to use the equation Q equals mc delta T to calculate that change of energy. But when you're on a plateau and a change of state, you'll notice that because it's a plateau, that the temperature is not changing, which means you can't use this Q equals mc delta T equation because you would get zero energy change, but we know that we're adding energy. So instead, you have to use Q equals m delta H. And when you're melting, it's going to be a delta H of fusion. And when you're boiling a substance, it's going to be delta H of vaporization. And the other thing that happens is, what the heck is going on with your intermolecular forces? Well, when you're going from a solid to a liquid, you're disrupting the intermolecular forces. So they're getting weaker on these plateaus. So you're weakening the intermolecular forces. When you're melting, it's just weakening them. When you're boiling a substance, you're actually completely getting rid of removing the intermolecular forces, or overcoming all of them. So the delta H or vaporization is usually significantly higher than the delta H of fusion, because in the delta, when you're going from point B to point C here, you're really only weakening the forces. But when you're going from point D to point E here, you're pretty much removing all of the intermolecular forces, or adding enough energy to overcome all of them, with the exception of the van der Waals forces that are present in gases as well. So this is an example problem on how to calculate the energy that's required. So how much energy is required to change the temperature of 30 grams of ice from negative 10 degrees Celsius to 57 degrees Celsius? Well, the easiest way to start off is when you start with one of these heating curves, and because the substance is water, and we know that at the low plateau you're melting, or it's the opposite of which is the opposite of freezing process, and water does this at 0 degrees Celsius. And then at the top plateau, we know that we're boiling, which it happens at 100 degrees Celsius for water. So you go ahead and you label those 2 points on the axis, and then that allows you to work with the curve a little bit easier. So we're starting at negative 10 degrees Celsius, so that's somewhere below this first plateau. So I'm just going to put a little hash mark there and mark the negative 10. And then we're going to 57 degrees Celsius, which is somewhere on the second plateau. And this kind of creates a little roadmap for you to follow when you're doing these calculations. And on the previous slide, we said that on an incline, so we're going from this point here all the way up to the other hash mark. And every time we change directions on this graph, we're going to have to change equations. So the first equation that we're going to use will take us up to point B here. So because that's an incline, we're going to use Q equals mc delta T. And so the mass that we have, we get directly from the problem that it's 30 grams. And the specific heat capacity of ice, and it's ice at this point because it's a solid on the lower incline. And so if you look it up, you will find that the specific heat capacity of ice is 2.03 joules per gram degree Celsius. And then the delta T is just the change in temperature for this tiny itty bitty little piece here. And so that's why we labeled these, another reason why we labeled these points on the axis. So we remember that that plateau is at 0 degrees. So the difference between the starting point and the plateau is 10 degrees Celsius. So we're going to have a 10 degrees Celsius temperature change here. And when I multiply 30 times 2.03 times 10 degrees Celsius, I get 610 joules. And we should have 2 sig figs because that temperature change has 2 sig figs in it. And then the next part I'm going to highlight this line with a green, and change the color so you can tell which part I'm on. And so in this next segment on that green line, you're going to have, it's a plateau, so we have to use Q equals m delta H. And because it's on the bottom plateau, it's going to be m delta H of fusion. So once again, our mass is 30 grams. And our delta H of fusion, if you look up the delta H of fusion for water, you'll find that it's 334 joules per gram. And when you punch that into a calculator, you multiply 30 times 334, you get 10,020 joules. You get 10,020 joules. Then the last part is going to be, the last part of our work is going to be this part that I'm highlighting in pink right now. And that's back to an incline again, so we're going to use Q equals mc delta T. Our mass is still 30 grams. our specific heat capacity, you have to look that up. And when you look up the specific heat capacity of liquid water, you get 4.18 joules per gram degree Celsius. And then the temperature change, remember that this plateau is at 0, so 0 to 57, that temperature change is 57 degrees Celsius. And when you punch all of that into a calculator, you get 7,100 joules. So the last step of all of this is to add these three numbers together. You add the 610 plus 10,020 plus 7,100, and you end up with 17,700 joules. And so that is my final answer, 17,700 joules. The next thing we have to talk about is vapor pressure. And while this might not seem like it has a whole lot to do with phase changes, it actually has a lot to do with phase changes, because the vapor pressure determines the temperature at which something will melt or freeze or boil or condense. So before we talk about how that affects it, though, we need to talk about vapor pressure itself and determine what it is. So vapor pressure is the pressure of a gas above the liquid of the same substance. And that's a partial pressure. So how vapor pressure occurs. When you first put a liquid in a container, all the particles of that liquid are in the liquid state. So you see here, this is the initial state. This is what you have initially, where all of the all the particles are in the liquid state, and they're held there by the intermolecular forces that substance has. But as time goes on, there's enough energy in the room and the environment at that temperature that the particles escape from the liquid state and enter the gaseous state. Eventually, what will happen is, and so you see here that there's particles in the gas state in this one here. Eventually, what will happen is that the particles, though, will the gaseous particles re-enter the liquid state as well. And that process goes back and forth. So you have a liquid going to a gas, and then the gas going back to the liquid. And eventually what will happen is that the rate at which the particles enter the liquid state and the rate at which the particles enter the gaseous state is going to be equal, and that's when we reach equilibrium. So the two rates will be equal, so you're not going to see a change. The pressure when this happens is the vapor pressure. So more on vapor pressure. Something is considered volatile if it has a high vapor pressure. And if it has a high vapor pressure, that means it enters the gas state rather easily. Because if it has a high vapor pressure, that means that there's more particles in the gaseous state, causing a larger pressure. So the particles move from the liquid state to the gas state easily. And this is the volatility of a substance is determined by the size of the intermolecular forces. So the higher the intermolecular forces, the lower the vapor pressure. So this is actually an inverse relationship. They are inversely related. And then in contrast, the lower the intermolecular forces, the higher the vapor pressure. And again, that's because there's not a whole lot holding the gas particles or the particles in the liquid state, so they enter the gas state really easily. The higher the mass, the less volatile a substance is, and that's because of the larger London dispersion forces. The same thing is you're going to have substances that have hydrogen bonding are going to tend to have lower vapor pressure, and if you have two particles of similar mass, then the one with the larger intermolecular forces will have a lower vapor pressure. And vapor pressure also increases with higher temperatures. So at higher temperatures, particles have more energy. And so the more energy they have, the easier it is for them to get into that gas state. And again, the more particles that are in the gas state, the higher the vapor pressure. And how does this all relate to phase changes? It comes into play with phase diagrams. So a phase diagram is a graph that shows the states of matter for a substance as a function of temperature and pressure in a closed system. And that pressure is actually the vapor pressure. So this is what a phase diagram looks like. And so you have pressure on the y-axis and temperature along the x-axis. And then you see these lines, and that's states of equilibrium. So some important things to know about phase diagrams. The first thing to take note on a phase diagram is where to find the different states of matter. So you'll see that on the left here, you have your solids. In the middle, or on the top right, you have your liquids. And on the bottom is where your gases are. So what that means is that at low pressure and low temperature, you can have a gas, the substance is going to be in a gas state. At higher temperature, at higher pressures, at low temperatures, they're going to be at a liquid state. You raise the temperature at that pressure and it's going to enter a liquid state. Next thing that you need to know are the lines. So the boiling condensing line, well, when a substance boils, it goes from a solid or liquid to a gas. So the boiling and condensing line is going to be the line that's separating the liquids and the gases. And the next line is the freezing melting line. So when a substance freezes or melts, it's going from between a solid and a liquid. So the line separating the liquid and the solid shows all the temperatures and pressures at which the substance will freeze or melt. And then the last part is the sublimation line, and that is the line separating the solid and the gas. And again, that's all the combinations of pressures and temperatures at which a substance will sublime. The triple point is the temperature and pressure at which all three phases can exist simultaneously. And that's right there where all of those lines intersect. Some more key points is that there's a critical temperature, and that is the temperature above which the vapor cannot be liquefied. So it doesn't matter how much pressure you apply, it's just not going to become a liquid anymore. And then critical pressure is the pressure needed to liquefy the substance at the critical temperature. So, and where the two of those meet, right here, is called the critical point. So that's the point where the critical pressure and temperature meet. And so you see when you look at the graph that past this point, it doesn't matter how much pressure you add, that substance is always going to be in the gaseous state. So you can see that the normal melting point is a temperature at which the solid and liquid have the same vapor pressure under conditions where the total pressure is 1 atm. So really what that means is the normal melting point is the temperature at which the substance will melt when the pressure is 1 atm. So to find, when you look at this graph, to find what the normal melting point is, you find where 1 atm is, you go over, and you find where it hits the line between the solid and liquid, and that's going to be the temperature at 1 atm at which it should normally melt at. You can do the same thing with the normal boiling point, and that's the temperature at which the vapor pressure of the liquid is exactly 1 atm. And so that's when you have 1 atm of pressure, that's the pressure at which the temperature at which it'll boil at. And that's the normal boiling point. But what happens when you lower the pressure? So if you lower the pressure from 1 atm, you can actually get a liquid to boil. If you look at this point right here, you can see that it's at a lower temperature than the normal boiling point, but it's also at a lower pressure. So you can actually get a substance to boil at a temperature that is lower than 1 atm. So I'm about to show you a video of the water boiling at room temperature. And here you can see we're in our classroom. This contraption at the back is called a vacuum pump, and it removes the air from the bell jar that we have here. And you can see the beaker of water. Because it's at room temperature, it stays at room temperature the whole time. There's no heat source on this water at all. So I'm going to play the video, and the obnoxious noise that you hear in the background is the vacuum pump running. So here it goes, and I apologize for the poor camera work because I'm holding the camera as I'm manipulating everything. So you can hear that noise, and the pressure is not getting changed, so I had to go and close the valve on that. Once the valve got closed, you can hear it's taking the air out of the bell jar, and that's lowering the pressure. And all of a sudden, you can look and you see really tiny bubbles forming. Those really tiny bubbles start to get bigger and bigger, and now you can see that the water is actually boiling. In just a second, I'm going to turn off the vacuum pump. So I turned off the vacuum. I'm turning off the vacuum pump here. I am going to reintroduce air into it so that I can actually open up the bell jar. Then I'm going to put my hand into it to prove to you that it is still at room temperature. If this was at 100 degrees Celsius, you would hear me screaming when I put my hand into it. But you can see it is 100% safe and totally comfortable to put my hand in. Right, so some more information that you can find on phase diagrams that's cool is you can tell when you look at the melting line, and again that's the line right here between the solid and the liquid. It'll actually tell you which phase is more dense. So if you have a positive slope of the melting line, and there's not much slope to this, but it almost looks like it's an infinite slope, but it's slightly positive. So the idea is that if you add pressure, if you increase the pressure of a substance, that means you are increasing the density of it. Because if you add pressure to it, you're squishing the particles together. So if you keep it at the same temperature, if you keep the substance at the same temperature, like right here, and you add pressure, and if you go from a solid, when there's a positive slope of the melting line, this line here, then you go from the liquid state to the solid state when you add pressure. Well, that means you've increased the density, right? So that tells you that the solid state is more dense than the liquid state. And this is true with most substances. Okay. However, you can also sometimes see a negative slope of the melting line. And here's a case of water, which actually has a negative slope, the slope of the melting line. So if I start at a given temperature, extremely close to that line, and I increase the temperature, eventually you're going to see, if I go up high enough, you would see that I go from the solid state to the liquid state. I actually move from the solid state to the liquid state, which means that the liquid state is going to be more dense. Because again, when you increase the pressure, you're really increasing the density as well, because you're squishing those molecules together closer, and so when it goes from a solid to a liquid, when that happens, that tells you that the liquid is more dense. So there are some times when things don't happen as they would be expected or predicted by these curves. So one of those cases is supercooling, and that's when a liquid exists below the freezing point. So you can actually have, what that means is you can have liquid water exist below 0 degrees Celsius. And that's because something is preventing the liquid from becoming organized enough to freeze. You can also have superheating, and that's when the liquid exists above the boiling point. And that occurs because the gas molecules do not organize readily enough to form a bubble. So if you have any questions, that's all I have for you on phase changes. So if you have any questions, please make sure you bring those questions to class.